A razor blade cannot slip between stones fitted thousands of years ago. This is the impossible precision of ancient construction, a global mystery carved into mountains and deserts. By the end, you will see human history not as a slow climb, but as a story punctuated by flashes of genius we struggle to explain. How did cultures without steel or silicon achieve alignments and fits that rival our best machines? And what forgotten knowledge vanished with them? What does true mastery over the physical world actually look like? High on a wind-swept plateau above the old Inca capital, a fortress wall rises from the earth like the jawbone of a giant. This is Sacsayhuamán. To stand before it is to feel a profound sense of scale, not just of the structure, but of the mystery itself. The stones are massive, some weighing over 100 tons, yet they are fitted together with a precision that defies their rough, organic shapes. Run your hand along the joints, and you will find no gap, no space for even the thinnest paper to slide through. The wall is a three-dimensional puzzle carved from granite, each piece unique, each locking perfectly with its neighbors without a drop of mortar. The central enigma is as solid as the rock itself. How did a civilization without iron, without the wheel for transport in this terrain, achieve such flawless, interlocking construction? And why has it survived centuries of powerful earthquakes that have toppled modern buildings in the valley below? Archaeologists point to a technique often called the cut and try method. It sounds deceptively simple. A stonemason would painstakingly shape a stone, then lower it against its neighbor, checking the fit. The high points where the rocks touched would be marked, ground down, and the process repeated over and over for what could have been months for a single block. They used what they had, string for measurement, water and sand as abrasives to slowly wear the hard granite into submission. This was not a quick process. It was an act of profound patience and communal effort, a conversation between human intention and the stubborn character of the mountain. The result is what we call polygonal masonry, a style where irregular polygons fit together in a network of seams that zig and zag in every direction. And this very irregularity is the secret to its strength. During an earthquake, a straight joint is a line of weakness, a place where energy can focus and crack the wall. But these labyrinthine joints diffuse the seismic energy, causing the stones to literally dance in place, settling back into perfect alignment once the shaking stops. It is a brilliant, built-in shock absorber conceived long before the science of seismology existed. To grasp the level of skill involved, consider a modern comparison. Today, we can cut stone with diamond-tipped saws and lasers to create a perfectly straight, seamless joint between two blocks. It is a marvel of engineering. Yet the Inca fit is more complex. It is not one straight plane, but a convoluted, three-dimensional surface that mates perfectly with another uniquely convoluted surface. Achieving that with primitive tools represents a different kind of mastery, one rooted in an intimate, tactile understanding of material. It forces us to ask a deeper question. What did the Inca know about stone that we, with all our technology, have perhaps forgotten in our rush for efficiency? Their precision speaks of a philosophy where the builder listened to the material, where time was not an enemy but a tool, and where resilience was woven into the very fabric of their architecture. This intimate, monumental precision sets the stage for a mystery on an even grander scale, where the stones are not just fitted, but orchestrated across a landscape with celestial ambition. The same philosophy of listening to stone echoes across the world in the dry air of the Egyptian desert, but here it was applied to a material that laughs at simple tools. Granite, this is not a soft limestone you can shape with patience. It is one of the hardest stones on the planet, a crystalline fortress. And yet, inside the very heart of the Great Pyramid, in the solemn space known as the King's Chamber, builders worked this unforgiving material to a standard that halts modern engineers in their tracks. The walls are constructed from enormous blocks of red granite, some weighing over 70 tons, hauled up from quarries hundreds of miles to the south. The surfaces of these monolithic slabs are not merely flat, they are flawlessly planar over distances of several meters. Engineers who have surveyed them note that the joints between these colossal blocks are so tight that the gap measures less than a millimeter in places. That is the thickness of a credit card. To achieve such flatness and parallelism on granite, with the tools archaeology traditionally assigns to the Old Kingdom, seems to border on the alchemical. The official toolkit consists of copper saws, which are softer than granite, and stone pounders made of dolerite. A copper saw alone would simply dull against the unyielding quartz crystals within the granite. So how was it done? The leading theory involves a clever marriage of material science and relentless labor. The Egyptians likely used those copper saws and drills not as cutting tools, but as delivery systems for something far harder, crushed quartz sand. By adding this abrasive slurry between the copper blade and the granite, and using a back-and-forth sawing motion, they effectively turned the sand into millions of microscopic cutting teeth. The copper simply held the abrasive in place, wearing away itself in the process, while the harder quartz sand slowly, inexorably, gnawed its way through the granite. Water may have been added to create a paste, carrying away debris and keeping the process cool. This method works, but it redefines our understanding of scale and effort. To cut a single block for the sarcophagus using this technique could have consumed months of continuous work, requiring teams to labor in shifts, constantly replenishing the abrasive slurry. The logistics become a breathtaking puzzle. Each multi-ton block had to be quarried with this painful slowness, then loaded onto barges for a journey down the Nile, then dragged across the desert plateau, and finally raised to a height of nearly 50 meters within the pyramid's rising structure, all without damaging those millimeter-perfect surfaces. The sarcophagus inside the chamber itself is the ultimate testament to this control. It was hollowed out from a single, solid block of granite, its internal corners carved with a sharp, precise 90-degree angle. Creating such a clean internal corner in granite with simple tools is an exercise in almost unimaginable skill and planning. It forces us to move beyond just the how of the cutting technique and to confront the who behind the operation. What kind of project management existed 4,500 years ago? What system of measurement and quality control ensured that a block shaped in a distant quarry would fit perfectly against a block already placed in the pyramid's core weeks or months later? This points not to a haphazard work site, but to a standardized, rigorously enforced system of precision that permeated the entire supply chain, from quarryman to final mason. The precision of the pyramids is not just in the cut of a stone, it is in the mind of the civilization that orchestrated it. This mastery over hard stone with soft metal tools presents us with a tangible, physical paradox, one that leads our search for answers from the monumental to the miniature to the tools themselves. But the mystery of cutting granite runs deeper than the surface, into the very heart of the stone itself. In the dusty storerooms of museums lie objects that present an even more confounding puzzle. Among them are granite cores, cylindrical pieces of rock drilled out by ancient craftsmen. One famous example, recovered from a site in Egypt, is particularly telling. It is a rod of granite about the thickness of a fist, and along its length run a series of perfectly symmetrical, spiral grooves. To a modern machinist, those grooves tell a clear story. They indicate a drill bit that advanced into the solid stone with immense, consistent pressure, turning at a steady rate and removing material in a continuous, uniform curl. The precision of these grooves is startling. They are evenly spaced and deep, suggesting a feed rate, that is, the speed at which the drill penetrated the stone, that rivals what we might achieve today with industrial diamond-tipped equipment. This is not the rough, chipped hole you would expect from pounding with a stone. This is the signature of a sophisticated machining process. The technique is known as tubular drilling. Imagine a hollow copper tube, its end pressed against the granite. As the tube is rotated, perhaps by a team of workers using a large bow drill apparatus or even a simple lathe-like device, an abrasive slurry of quartz, sand, and water is fed into the contact point. The tube does not cut the stone, the sand does, grinding away a circular channel. As the tube sinks deeper, it leaves behind a solid core of stone inside it. To remove that core, the ancient workers would have driven wooden wedges into the channel around it, swelling the wood with water to crack the core free from the surrounding block. Evidence of this practice is etched into history. Look at the unfinished obelisk in Aswan, still lying in its granite quarry. You can see where workers began to separate this colossal needle from the bedrock by drilling a line of these tube holes along its base. Or examine the interiors of the hard stone sarcophagi, where the hollowed-out spaces for the lids show the telltale marks of this drilling method. Experimental archaeologists have tried to replicate the process. Using a reconstructed copper tube, a bow to spin it, and quartz sand, they have managed to drill into granite. The grooves they produce are similar, but there is a telling difference. The ancient cores often show a much faster feed rate. The grooves are spaced farther apart, meaning the drill bit sank into the incredibly hard stone more quickly than their best reconstructions can achieve. This gap between experiment and artifact is where the true enigma lies. It forces a difficult question. Was this simply the pinnacle of a long, lost tradition of trial and error, where generations of craftsmen refined their slurry mixtures and drilling rhythms to an art form we have yet to fully replicate? Or do these spiraling grooves hint at a level of mechanical advantage, a forgotten technology for applying tremendous, steady pressure that has since vanished from the historical record? The cores are silent, but their testimony is written in stone. They speak of a civilization that did not just move mountains, but commanded them to open up, to yield perfect cylinders from their solid mass. This profound manipulation of material connects directly to a final, breathtaking expression of ancient precision, one that moves beyond construction and into the realm of transcendent art. The spiraling grooves in those granite cores hint at a control over stone that feels almost surgical. But what if ancient builders possessed an even more profound secret, a way to bypass cutting and drilling entirely? Across the world, from the high Andes to the jungles of Southeast Asia, indigenous stories whisper of a forgotten art, the ability to soften stone itself. Legends speak of a special plant, a sap or a juice, that when applied to rock would make it pliable like clay, ready to be molded into impossible shapes before hardening back into its original, unyielding strength. To modern ears, it sounds like pure fantasy, a myth born from awe. Yet, when you stand before certain ancient sites and run your hand over surfaces that appear melted, poured, or sculpted with a fluid grace, the question becomes hauntingly tangible. Could there be a lost thread of chemical or botanical knowledge that explains what our tools seemingly cannot? This idea moves us into one of the most speculative and controversial frontiers of ancient construction studies. It challenges our most basic assumptions about how these civilizations worked. At sites like Puma Punku in Bolivia, the stonework presents a particular enigma. Here, andesite blocks, a stone as hard as granite, are carved with geometric complexity that looks machined. You see precise, repeating notches, razor-sharp inner corners, and surfaces of uncanny flatness. Some of the stones have intricate, interlocking channels that seem less carved and more cast. This has led some researchers to explore a radical theory, geopolymerization. This is the idea that ancient builders did not just cut stone, but created it, mixing a kind of ancient concrete from crushed rock and a natural binder to pour or mold these forms. Proponents point to the lack of visible tool marks on certain surfaces and the seemingly uniform texture of the stone as potential evidence. Mainstream archaeology remains deeply skeptical, citing the clear evidence of quarrying and tool work found at these very sites. The truth likely lies in a sophisticated middle ground. Materials scientists have entered the conversation, examining whether certain natural compounds could have given builders a temporary advantage. Research has looked at the properties of organic acids found in some plants, like oxalic acid, which can slowly degrade silicate minerals, the building blocks of granite and similar stones. Over time, applying such a substance could create a softened, gel-like layer on the surface, a layer that might be easier to work with abrasives or even to impress with molds. Specific plants are often cited in these old stories. One, known as the Queen of the Night Cactus, or Epiphyllum oxypetalum, has been rumored in various traditions to possess such properties. The challenge is that no modern experiment has definitively proven that these plants can soften hard stone to a workable degree in a practical time frame. Experiments have shown mild etching or surface alteration, but not the legendary clay-like malleability. So if not literal softening, what could explain the molded appearance and machine-like precision at places like Puma Punku? The answer may force us to expand our definition of advanced technique. Imagine a process of ultra-precise abrasion, where craftsmen used harder stone tools and specialized sanding slurries not just to flatten a surface, but to carve complex, interlocking geometries through a template system. This would require an extraordinary understanding of measurement and geometry, a kind of Stone Age CD system executed by hand. Alternatively, consider a form of lost wax casting, but for stone. If a clay or earthen mold could be created with perfect negative shapes, perhaps a slurry of crushed stone and mineral binder could be packed into it, creating a hardened, artificial stone block that fits a predetermined design with perfect accuracy. This would be a form of geopolymerization, but on a smaller, more artistic scale rather than for entire megaliths. These speculative ideas push us to look beyond the how of construction and into the why of such obsessive geometry. The perfect angles, the seamless joints, the repeating patterns, they all point to a cultural imperative that valued precision as something more than structural. It was perhaps a language, a way to encode harmony, astronomical alignments, or sacred principles into the very bones of their world. The stones at Puma Punku are not randomly shaped. Their forms are deliberate and complex, suggesting a blueprint of immense sophistication. Whether achieved through a forgotten chemical process, a pinnacle of abrasive skill, or a revolutionary casting technique, the result stands as a monument to a way of thinking about material that we are still struggling to fully decipher. This pursuit of perfect form leads us inevitably to a final, overarching question, one that ties all these global mysteries together. The sun does not simply rise over Stonehenge on the summer solstice. It performs a ceremony written in stone 5,000 years ago. As dawn breaks, a single spear of golden light passes perfectly through a narrow gap between the outer sarsen stones, strikes the heel stone, and floods the central altar with illumination. This is not an accident of architecture. It is a deliberate, breathtaking alignment, a clock built for a god. This phenomenon is part of a global language written not in words, but in the positions of megaliths, a field of study known as archaeoastronomy. From the deserts of Egypt to the mesas of the American Southwest, our ancestors encoded the movements of the sun, moon, and stars into the very bones of their landscapes with a precision that humbles our modern disconnect from the sky. Consider the sheer scale of the task. These builders had no telescopes, no written star charts as we know them, and no understanding of the heliocentric solar system. Their tools were their eyes, simple markers like wooden posts or standing stones, and generations of patient, meticulous observation. The cycles they tracked are not simple. The sun's rising and setting points shift along the horizon throughout the year, reaching their northern and southern extremes at the solstices. The moon follows a more complex 18.6-year cycle, its extreme rising points slowly migrating. And over a vast period of 26,000 years, the entire celestial sphere slowly wobbles, a phenomenon called precession, which gradually changes which star marks the North Pole. To build a structure that remains aligned to a specific celestial event over centuries, you must account for this slow drift. You are not building for your own generation. You are building for your descendants 1,000 years hence. The examples of this encoded knowledge are staggering. The Great Pyramid of Giza is aligned to the cardinal directions with an error of just a fraction of a single degree, a feat of surveying that rivals modern instruments. In the Chaco Canyon of New Mexico, a spiral petroglyph high on Fajoda but becomes a precise solar calendar. At noon on the summer solstice, a dagger of sunlight slices perfectly through the center of the spiral, a phenomenon known as the sun dagger, marking the year's pivotal moment. In Ohio, the Great Serpent Mound, with its undulating earthwork body, aligns to the setting sun of the summer solstice, while its coiled tail may point to the extreme rising points of the moon during its major standstill. How was this possible? Let us walk through the process a Neolithic astronomer might have used. The simplest tool is a gnomon, a straight stick placed vertically in the ground. Each day you mark the tip of its shadow at noon. Over a year, these marks trace a pattern, with the longest shadow at the winter solstice and the shortest at the summer solstice. By repeating this process year after year, you can pinpoint the solstice days with increasing accuracy. To capture a sunrise alignment, you would place a distant marker, like a large stone, on the horizon where the sun rises on the solstice. Once that sightline is fixed, you can build your monument to frame it. This requires not just individual genius, but a cultural tradition that values and preserves this data across lifetimes, a living library of the sky. This leads to the profound reflective question: why go to such extraordinary lengths? Was it purely practical, a giant agricultural calendar to ensure planting and harvest? Was it for religious ceremony, to create a theater where the divine light of the cosmos physically touched the human realm? Or was it something deeper, a philosophical statement that humanity is not separate from the universe, but an integral part of its cycles? The precision suggests an answer encompassing all three. By mirroring the cosmos on Earth, they created a sacred geography, a place where myth, survival, and the stars were woven into a single tapestry of meaning. This celestial cartography, this ability to map the heavens onto the land, finds a parallel in another ancient skill, the mapping of the Earth itself with an accuracy that seems equally out of place in time. Legends from the Andes to the Nile speak of stones that sang themselves into place. In these old stories, priests or wise ones would chant, play sacred instruments, or strike certain rocks with hammers, and the massive blocks would lose their weight, gliding through the air as if on water before settling gently onto a waiting wall. It is a beautiful myth, a poetic explanation for the impossible. But what if this folklore holds a faint, distorted echo of a real and forgotten physics? Modern science offers a fascinating bridge from that myth into the realm of plausible principle through the study of acoustic resonance. We know that sound is a physical force, a pressure wave moving through air or material. At specific frequencies, these waves can create standing wave patterns, points of high pressure and low pressure that are stable and powerful. In laboratory settings, physicists have used precisely tuned speakers to create such standing waves, allowing them to acoustically levitate small objects, like droplets of water or tiny pieces of polystyrene, holding them suspended in midair. The object is trapped at the nodes, the points of minimal pressure between the intense sound waves. This is not magic, it is demonstrable science, though it requires immense precision and control. Scaling this phenomenon up to levitate a stone weighing tons is, with our current technology, a fantasy of energy requirements. The power needed would be astronomical. Yet, this line of inquiry opens a more subtle and intriguing possibility. Perhaps the ancient secret was not full levitation, but a radical reduction of friction. Imagine a multi-ton block resting on a bed of sand or a specially prepared track. If you could find the resonant frequency of that stone itself, the specific pitch at which it naturally wants to vibrate, and then bombard it with that sound using large drums, chanting voices, or struck monoliths acting as natural amplifiers, something remarkable could happen. The intense, sympathetic vibration could momentarily fluidize the interface between the stone and the ground. The particles beneath it would act less like a solid and more like a liquid, drastically reducing the sliding friction. The colossal block might then be moved by a surprisingly small crew pushing in rhythm with the pulses. This idea moves us from pure myth into speculative engineering. It finds its most famous modern proponent in the strange story of the Coral Castle in Florida. In the early 20th century, a single man named Edward Leedskalnin, who stood just 5 feet tall and weighed 100 pounds, claimed to have discovered the secrets of the pyramids. Working alone at night, he single-handedly quarried, shaped, and positioned over 1,000 tons of coral rock into gates, walls, and astronomical sculptures. How did he do it? He was famously secretive, only saying he understood the laws of weight and leverage, and some visitors reported hearing him sing to the stones. While his achievement is more a modern folk mystery than an ancient one, it fuels the question of whether a profound, empirical understanding of vibration and balance could grant a form of practical leverage we have overlooked. Consider the acoustic environment of an ancient quarry. Granite, when struck, rings with a clear, bell-like tone. Different sized stones have different resonant frequencies. What if the master builders learned to listen, to tune their efforts to the stone's own voice? By striking a quarry face with a hammer at the right rhythm, they might have found frequencies that caused cracks to propagate more easily or made the stone seem to yield. Some researchers have pointed to the massive trilithon stones at Baalbek in Lebanon, each weighing around 800 tons. The local quarry, where an even larger 2,000-ton monolith lies abandoned, has an acoustic quality. The act of many workers chanting in unison while using ropes and levers would not just coordinate their labor, it could have created a low-frequency vibration that traveled through the ground, perhaps helping to break the stone's bond with the bedrock or ease its initial movement. Modern experiments give a glimpse of the principle. Engineers have shown that by vibrating a heavy object at a specific frequency while it sits on a thin film of lubricant, they can drastically reduce the force needed to slide it. The vibration essentially turns the surface into a temporary, near-frictionless plane. This is a far cry from mystical levitation, but it is a powerful, physics-based technique. So we are left with a reflective challenge. Could these scattered legends of singing stones represent a deep, empirical science of acoustics and material resonance, developed through millennia of trial, observation, and lost oral tradition? Did ancient builders discover that everything, even a mountain, has a song, and that by singing back to it in the right key, they could enter into a kind of cooperative dialogue with the material world? This shifts our perspective once more. It suggests the intelligence behind these sites may not have been solely in the blueprint or the muscle, but in a holistic sensory awareness, an ability to perceive and harness forces we have only recently begun to measure with instruments. This holistic awareness of unseen forces finds a parallel in the final, and perhaps most personal, mystery of all, the tools that left no trace. A master builder stands on a virgin site, the desert floor stretching before him, tasked with laying the perfect square base for a pyramid that must align with the cosmos. He has no laser levels, no satellite surveys, not even a sheet of papyrus for a detailed architectural drawing. This is the silent, invisible frontier of ancient genius, the planning phase. How do you design, communicate, and execute a project of staggering complexity and precision across decades, ensuring that 1,000 workers all share the same vision? The answer lies not in a single blueprint, but in a sophisticated system of physical models, embodied mathematics, and rigorous standardization. Archaeologists have found clues to this process. Small-scale models of temples and tombs carved from wood or stone have been discovered. These were not mere toys, they were the three-dimensional contracts between priest, king, and builder. A master craftsman could use such a model to demonstrate proportions, to calculate volumes of material needed, and to teach his teams the essential relationships of the structure. But for the actual laying out of the building on the ground, they turned to geometry made physical. The primary tool was likely the humble, yet profoundly powerful, knotted cord. Imagine a long rope with knots tied at precise, standardized intervals, a measuring tape woven from hemp, using stakes, sighting rods, and the immutable truths of right-angled triangles. A surveyor could transcribe perfect geometry onto the chaotic reality of the landscape. To create a perfect north-south meridian line, they could have used the stars, tracking the shadow of a vertical gnomon over the course of a day. To lay out a perfect square base for a pyramid, they might have employed the classic 3-4-5 triangle method. They would stretch a cord with 12 equally spaced knots, forming a loop, by pegging down the cord at the knot marking 0, then stretching it to create a triangle with sides of 3 knots, 4 knots, and 5 knots. They would guarantee a perfect 90-degree angle at the corner. Repeating this process would create a geometrically flawless square, hundreds of feet on a side, on ground that was far from level. This was applied sacred geometry, where mathematical constants were not abstract numbers but living principles built into the fabric of their world. We see this encoded intelligence in the very proportions of the Great Pyramid. The ratio of its perimeter to its height is remarkably close to 2 times pi. The use of the royal cubit, a standard measure of about 20.6 inches, ensured every team from quarry to construction site was singing from the same mathematical hymn sheet. This was a civilization that thought in ratios and harmonies, seeing the same patterns in the human body, the motions of the planets, and the ideal temple. The discovery of artifacts like the disassembled cedarwood Khufu ship buried in a pit beside the pyramid offers another window into this planning mind. Its over 1,200 pieces were meticulously labeled and organized, a kit to be assembled in the afterlife. This reflects a mindset of extreme systematic organization, an ability to break down a complex whole into manageable, logical components, store them, and reassemble them flawlessly years or even generations later. It is a perfect metaphor for their architectural process. So what does this level of systematic, pre-construction intelligence imply about their society? It speaks of a highly stratified, specialized civilization with a powerful central authority. There were not just laborers, there were master surveyors, overseers of the royal cubit, keepers of the standard models, and accountants of stone. Knowledge was compartmentalized, passed down through guild-like families, forming a living library of technique. The project manager of the pyramid was not just an architect, he was a high priest of logistics, a conductor of human and material orchestras playing a symphony that lasted longer than a lifetime. This invisible framework of planning and proportion is what made the physical miracles possible. It was the operating system for their ambition, and it forces us to ask, if their planning was this advanced, what of the tools that executed those plans? We have marveled at the stonework, but the very instruments that shaped that stone present a final, intimate puzzle. The copper chisels found in royal tombs are elegant, ceremonial, and utterly useless for the task history assigns to them. This is the quiet scandal at the heart of Egyptology. We have the soft metal tools, and we have the impossibly hard stone they were supposed to shape, but the two do not match. The beautiful copper implements would blunt into useless nubs after just a few strikes against granite's crystalline fortress. So where are the real tools, the ones that did the work? This is the enduring case of the missing hard tools, a mystery that forces us to question what has been lost to time, or what we are simply failing to see. Metallurgists step into this gap with fascinating possibilities. First, there is work hardening. If an artisan took a copper chisel and repeatedly hammered and annealed it, cooling and reheating it with care, the metal's crystalline structure could be altered, making its edge significantly harder and more durable. This is a known ancient technique, but the question remains whether even work-hardened copper could withstand the prolonged, punishing contact with quartz-rich granite needed to create the surfaces we see. Could there have been an unknown alloy, a blend of copper with another mineral that created a bronze-like material long before the traditional Bronze Age? Or perhaps the answer is not metal at all, but stone itself. Archaeologists point to dolerite pounders, fist-sized balls of a volcanic rock harder than granite, found in abundance at quarry sites. These could have been used in a relentless pounding technique to pulverize the granite along a desired line. But this method seems too crude for the millimeter-perfect flatness of the pyramid's interior stones. The true clues are not in the toolboxes we have found, but in the marks left on the stone itself. The wear patterns are a forensic record. On some granite surfaces, you see long, straight striations, parallel lines that suggest the back and forth motion of a saw. On the famous drilled cores, we see those spiraling grooves that speak of a rotating drill bit with immense, steady feed pressure. These marks tell us about motion and contact, but their fineness also hints at the composition of the cutting agent. The striations are often microscopically smooth, suggesting the abrasive slurry used, whether quartz sand or something harder like crushed emery, was of a consistent, fine grain. This points to a sophisticated understanding of abrasives, treating them not as dirt, but as an engineered cutting component. Then there are the enigmatic artifacts, the stones that seem to bear the fingerprints of something more advanced. At sites like the Serapeum of Saqqara, where massive granite boxes weighing over 70 tons rest in underground tunnels, the precision becomes almost unnerving. The surfaces of these sarcophagi are flawlessly flat, their corners sharp, and their interiors hollowed out with such geometric perfection that some engineers argue simple hand tools could not achieve it. The debate centers on the inside corners, where two flat planes meet at a perfect 90-degree angle. Creating that sharp, internal corner with a copper saw and sand would be extraordinarily difficult, as the saw would tend to round off the junction. This has led to speculation about the use of tubular drills not just for holes, but for cutting trenches, or even the use of straight saws that were somehow guided with jigs or frames to maintain absolute perpendicularity. At other global sites like Puma Punku in Bolivia or in the foundations of the Valley Temple in Egypt, you find stones with what appear to be precise, repeating grooves or cuts that look, to a modern eye, machined. These so-called machine marks fuel endless speculation, but mainstream archaeology urges caution. They could be the result of a highly refined, repetitive technique using a guided abrasive cord, like a wire saw, or a tool made from a rare, ultra-hard stone we have yet to identify. This brings us to the reflective core of the mystery. Are we underestimating the raw power of simple tools wielded with God-like patience and generational skill? Could a team of workers using nothing but dolerite pounders, copper rods, sand, and water achieve these results if given not months but years per block? The sheer scale of such an investment of time and labor is itself a kind of advanced technology, a societal commitment we can scarcely comprehend. Or is the opposite true? Could the real tools, perhaps made of iron or an advanced alloy, have been so valuable that they were endlessly recycled, melted down and reused until no trace remained in the archaeological record? Copper and bronze corrode, wood rots, and leather straps disintegrate. The most critical components of their tool kits, the frames, the guides, the lifting harnesses, may have left no trace at all. This tool debate is ultimately inseparable from the human hands that wielded them. It forces us to envision not a missing magic tool, but a missing magnitude of organized, skilled labor, operating with a unity of purpose and a repository of tactile knowledge that itself was the most advanced technology of the ancient world. The sheer volume of stone in the Great Pyramid is matched only by the volume of human life it consumed. Conservative estimates suggest its construction demanded something on the order of 2,300,000 individual stone blocks, and the labor to place them likely exceeded 20 million man-hours. This figure is not just an abstract statistic, it is a profound social equation. To translate that into reality meant housing, feeding, and coordinating a workforce that may have swelled to 20,000 people or more at the project's peak, not as a chaotic mob, but as a precision instrument. How do you turn tens of thousands of individual wills into a single, focused force capable of aligning multi-ton stones to a fraction of an inch? The answer lies not in whips and chains, but in a breathtakingly sophisticated system of logistics and social organization that was, in its own way, as precise as the masonry. For decades, the popular image was one of enslaved masses toiling under the lash, but the archaeological evidence paints a radically different and far more interesting picture. Excavations around the Giza Plateau have uncovered the remnants of extensive worker settlements, complete with barracks, bakeries large enough to feed thousands, and facilities for drying fish. The bones found in a dedicated cemetery nearby tell a story of skilled labor. Many show signs of healed fractures and sophisticated medical interventions, like successful amputations, indicating these individuals received care and were valued enough to be nursed back to health. This was not a population of disposable slaves, but a rotating workforce of conscripted laborers, likely farmers who worked on the project during the Nile's annual flood season when their fields were underwater. This system, known as corvée labor, was a form of national service, a duty owed to the state and the divine king. The motivation was complex, intertwining civic obligation with powerful religious belief. To contribute to the king's eternal vessel, his vehicle to join the gods was to participate in maintaining the cosmic order of Maat itself. It was an act of profound spiritual significance that guaranteed stability for the entire nation. This belief system was the glue, but the day-to-day operation was pure bureaucratic genius. A vast administrative hierarchy managed everything. Scribes tracked work gangs with names like Friends of Khufu or the Drunkards of Menkora, distributing daily rations of bread, beer, and fish. The scale of provisioning was industrial. The bakery complexes could produce thousands of loaves per day, and evidence of massive cattle slaughter indicates protein was a regular part of the diet, fuel for immense physical effort. This level of care was pragmatic, an investment in efficiency and morale. A healthy, motivated worker moves more stone. Now, apply this logistical machine to the single task of moving a 70-ton granite block from its quarry in Aswan to the rising pyramid at Giza, a distance of nearly 500 miles. The journey began with teams using dolerite pounders to free the block from the bedrock. Once loose, it was likely loaded onto a massive wooden sledge. We have tomb paintings showing this exact process, with workers pouring water or perhaps a slick slurry ahead of the sledge's runners to reduce friction. The block would be dragged to the Nile, a feat requiring a coordinated pulling team of dozens, if not hundreds of men, directed by foremen using rhythmic chants to synchronize their heaves. At the river, the stone was transferred to a specially built, heavy-duty barge. During the flood season, the Nile's higher water level would have helped carry this incredible load northward. Upon arrival near Giza, the process reversed, with the sledge team hauling the block up a specially prepared causeway to the construction site. Here, the real coordination began. Ramps, whether straight, zigzagging, or spiraling around the pyramid's growing face, provided the highway to the sky. Teams using ropes, levers, and possibly a system of counterweights would have inched the block upward, course by course. The synchronization required is staggering to contemplate. A misstep, a snapped rope, a loss of rhythm could mean catastrophe. This was human muscle organized into a living, breathing machine, every pull and push a calculated part of a decades-long symphony. It forces a reflective question about the nature of their society. What kind of social contract existed that could command such effort, not through terror, but through a blend of duty, belief, and tangible care? The engineering marvel is not just in the placed stone, but in the invisible architecture of trust, administration, and shared purpose that made placing it possible. This human-centered system of colossal yet precise effort stands in sharp contrast to a final, persistent question that whispers from the shadows of these sites. A question not about how they built, but about what or who might have shown them the way. A single, curious object can unravel an entire timeline. Scattered through museum archives and private collections are items that defy simple classification. Artifacts that seem to carry the fingerprint of a different age. These are the so-called out-of-place artifacts, objects whose material, design, or implied technology clash violently with the accepted history of the culture that supposedly made them. For those who study the limits of ancient precision, this fringe of inquiry presents a tantalizing yet treacherous frontier. What if the key to the mystery is not just lost technique, but a lost material? Imagine an archaeologist carefully brushing dust from a ceremonial dagger, only to have lab analysis later reveal traces of an alloy not invented for another 1,000 years. Or a stone block from an ancient temple that, when examined, shows evidence of a synthetic binder with properties we have only recently replicated. These are the sparks that ignite the most speculative debates. The field is a minefield of forgery, misidentification, and romantic projection, where a single anomaly is often inflated into proof of ancient astronauts or Atlantis. Yet, careful researchers note that dismissing every oddity out of hand is also unscientific. The true value of these anomalies lies not in proving fantastical theories, but in highlighting the gaps in our understanding and in forcing us to ask better questions. Take the famous Iron Pillar of Delhi, a 7-meter-tall column erected around the 4th century. For over 1,600 years, it has stood exposed to the elements with only the faintest layer of rust. Modern metallurgical analysis reveals its secret, a high phosphorus content which, combined with local climate conditions, promotes the formation of a thin, protective patina that actively resists corrosion. This was not magic, but a sophisticated, if perhaps accidental, feat of early material science. The knowledge of how to achieve this specific alloy composition, however, appears lost for centuries after the pillar's creation. Then there are the much more controversial finds, like the tiny, spiral-shaped objects unearthed from ancient riverbed deposits in Russia, some dating back tens of thousands of years. Ranging from a few centimeters down to microscopic sizes, these coiled filaments, mostly of tungsten and molybdenum, have been claimed by some to be evidence of micromachinery from a lost, advanced civilization. Mainstream geology offers a far more mundane, yet fascinating explanation. They are likely the byproducts of Soviet-era rocket testing from a nearby facility, where the intense heat of re-entry or combustion can create such peculiar fused metal forms. The lesson here is the paramount importance of context and rigorous peer review. An object without a clear, documented archaeological context is like a word without a sentence. Its meaning is impossible to reliably determine. The most compelling cases are not the isolated curiosities in a collector's cabinet, but the anomalies found in situ by reputable teams. This leads to a more concrete and increasingly respected area of study: ancient composite materials. Recent research into Roman concrete, for instance, has revealed a stunning form of ancient high technology that was right under our noses. Their seaport structures, exposed to corrosive seawater for 2 millennia, are not only standing but have grown stronger. Scientists discovered that the Romans used a mix of volcanic ash and lime, and that seawater reacting with this mixture over time actually grows rare, interlocking minerals that seal cracks as they form. This is a self-healing material, a concept at the cutting edge of modern materials science, perfected 2,000 years ago. Similarly, studies of the mortar used in some Inca structures suggest it may have contained organic compounds that allowed for slight, flexible movement, contributing to their legendary earthquake resistance. These are not out-of-place artifacts. They are proof of an in-depth, empirical knowledge of chemistry and material behavior that we are only now beginning to decode with advanced instruments. So how do we navigate this landscape? The challenge is a three-way fork. Is an inexplicable object evidence of a lost, sophisticated technology that arose independently and was later forgotten? Is it the product of a rare, anomalous natural process that we have not yet fully understood? Or is it simply a modern misinterpretation where we project our own technological world onto an object that had a completely different, perhaps ceremonial, purpose to its makers? Distinguishing between these possibilities requires a disciplined balance of open-minded curiosity and ruthless skepticism. It demands that we listen to the material evidence itself, not our desires for it. This fringe inquiry, for all its noise and controversy, ultimately circles back to the core theme of cultural knowledge transmission. It reminds us that our historical timeline is not a smooth, inevitable climb, but a fragile thread. Entire libraries of practical knowledge, from metal alloys to concrete recipes, can vanish in the upheaval of a society, leaving behind only the physical artifacts that whisper of a mastery we struggle to explain. These anomalies, whether ultimately explained or not, serve as vital reminders that the past is far less settled than our textbooks might suggest. The sea has spent 2,000 years trying to destroy the Roman harbor at Caesarea, and it has utterly failed. While modern concrete seawalls crumble in decades under the same relentless waves, these ancient structures endure not in spite of the water, but because of it. This is the secret of self-healing concrete, a material that defies time through a form of chemical intelligence. The Romans did not just build with rock and mortar, they engineered a living material, a testament to an advanced empirical mastery of chemistry that rivals their legendary feats in stone. Modern chemists, finally unlocking its secrets, describe it as a pozzolanic reaction. The recipe was deceptively simple: lime, volcanic ash from a region called Pozzuoli, and seawater. When mixed, the lime and ash formed a stable binder, but the real magic happened over centuries. As seawater slowly seeped into the concrete, it reacted with the volcanic ash to grow rare, interlocking crystals of a mineral called aluminous tobermorite. These crystals act like a microscopic immune system, filling cracks as they begin to form, creating a structure that grows denser and stronger with age. This was not an accident. Roman engineers observed that structures built with this specific volcanic ash near the Bay of Naples outperformed all others. They then systematically replicated the formula across their empire, shipping the key ingredient across the Mediterranean to critical ports. The knowledge was so precise and so effective that it vanished with the empire itself, leaving modern engineers to scratch their heads at concrete that performs better after 2 millennia than our own does after 50 years. This chemical precision was not unique to Rome. In the high Andes, Inca masons used a lime mortar in some of their most important structures. Analysis suggests it may have contained organic compounds, perhaps from plant sap, that gave it a slight flexibility, allowing walls to breathe and shift during earthquakes without fracturing. Far to the north, the Maya and other Mesoamerican cultures developed complex, plaster-like stuccos for their pyramid facades, mixes of burnt lime, sand, and water that were worked to a high polish, creating dazzling white surfaces that reflected the sun. These finishes were so durable that remnants still cling to temples after 1,000 years of jungle humidity. To understand the achievement, look through a microscope at a sample of Roman concrete. You would see not a static, crumbling matrix but a dynamic landscape. The crystals of tobermorite and another mineral, philipsite, form a labyrinthine network, a reinforcing web that blocks the propagation of stress cracks. Water attempting to penetrate actually triggers the formation of more crystals, sealing the breach. This is passive, automatic repair engineered on a nanoscale. What does this imply about the builders? It speaks of a science built not in laboratories, but through generations of meticulous observation and daring experimentation. Some anonymous Roman engineer, centuries before the Common Era, must have noticed that a mix made with the strange sand from Pozzuoli set harder underwater. He would have experimented with ratios, tested samples in tidal pools, and kept records of what worked. This knowledge was then codified, passed down through guilds, becoming a standard that built an empire's infrastructure. The reflective question is profound. How many such recipes existed? How many formulas for resilient plasters, flexible mortars, or super-hard alloys were part of the common knowledge of their day, only to be lost in the collapse of a dynasty, the burning of a library, or simply the slow erosion of oral tradition? This chemical mastery is the silent partner to the physical precision of cut stone. One shaped the block, the other bound the world together. It represents a different facet of the same ancient genius, a deep, practical dialogue with the very elements of the earth, seeking not to conquer nature, but to collaborate with its hidden properties. And this collaboration between builder and material finds its ultimate expression not in a mix, but in a method, a principle of working with mass and gravity that seems to defy physics itself. The same interlocking stonework that puzzles us at Sacsayhuamán appears on the other side of the world, in the ancient castles of Japan. Two cultures separated by an ocean with no known contact, both arrived at a startlingly similar solution: polygonal masonry. In Japan, it is called gangi-zumi, and seeing it creates a powerful sense of déjà vu. Massive, irregular stones fitted together with knife-edge precision, forming walls that have withstood centuries of earthquakes. This global echo forces a fundamental question upon us. When we see the same precise technique appear in distant lands, are we looking at the spread of a single, forgotten idea, or are we witnessing something innate in the human mind? Historians of technology point to a powerful concept: convergent evolution. In nature, dolphins and sharks developed similar streamlined bodies because the problem of moving fast through water has a limited set of optimal solutions. In human innovation, the same principle applies. When disparate cultures face a common, monumental challenge, like building earthquake-resistant structures from local stone, their ingenuity can funnel them toward remarkably similar answers. The Inca and the Japanese both lived in violently seismic regions. Both had access to large, hard stone, and both developed a method that sacrificed speed for immortality, choosing to spend generations on a wall that would never fall. Yet look closer, and the differences in their execution reveal the fingerprint of independent thought. The Inca technique, as we have seen, involved a patient, three-dimensional sculpting, creating that famous puzzle fit. The Japanese gangi-zumi style, while also polygonal, often shows a different approach. The stones were carefully selected for shape, then their facing surfaces were painstakingly dressed flat to create tight seams, but the backs of the stones were often left rough, keying into a rubble core behind the wall. The tool marks differ, the specific stone types differ, and the ultimate purpose differed, with Inca walls often being monumental and ceremonial, while Japanese walls were primarily military fortifications. This is not a copy, it is a parallel invention. This pattern of independent genius repeats across the ancient world. Monumental pyramid structures rose not just in Egypt, but in Mesopotamia, in Mesoamerica, and in what is now China. The pyramid form is not merely a tomb, it is the most stable way to build towering height with stone, a geometric solution to the problem of gravity that multiple cultures discovered on their own. The same is true for precise astronomical observatories, from Stonehenge to the Sun Dagger at Choco Canyon to the elaborate celestial temples of Angkor Wat. When humanity looks up at the same stars, the drive to map and mark their cycles seems to be a universal impulse. Consider the architectural triumph of the true arch. We associate it most famously with Rome, where it revolutionized construction, allowing for vast aqueducts and colossal amphitheaters. But the true arch was also invented independently in ancient Mesopotamia and later in China. The corbelled arch, a stepping stone toward the true arch, appears in the tombs of Mycenaean Greece and in the Maya structures of Central America. Different cultures, working through trial and error, discovered that by arranging stones in a particular way, they could make an opening that supported incredible weight, turning a wall into a gateway. What does this global chorus of parallel invention tell us? It challenges the simplistic idea that precision was a secret handed down from a single, lost master civilization. Instead, it speaks to a profound and shared capacity within humanity. When faced with the universal needs for shelter, for permanence, for connection to the cosmos, and for survival against natural forces like earthquakes, the human mind, in isolation, is capable of extraordinary leaps. The same materials, stone, water, sand, and human ingenuity, when focused on the same fundamental problems, can yield eerily similar masterpieces. This is not a diminishing of their achievement, but a magnification of it. It means that the drive for precision, for harmony with the natural world, and for building legacies that outlive empires is woven into our species. This global perspective prepares us to zoom in on one of the most iconic and debated examples of all, a site where every stone seems to whisper a different theory, and where the line between natural wonder and human intention becomes beautifully, frustratingly blurred. The scattered stones of Puma Punku do not look ruined, they look disassembled. Lying on a high plateau in Bolivia, these blocks of andesite and diorite, some weighing over 100 tons, present a visual language of precision so acute it feels anachronistic. Their edges are razor-sharp, their surfaces flawlessly flat, and they are carved with geometric complexity that seems machined, not hand-carved. This site, part of the larger Tiwanaku complex, is perhaps the most visually perplexing case study in the ancient world, a place where the stones themselves challenge our narrative of technological progress. Engineers who examine these blocks note features that defy simple explanation. There are H-shaped blocks with perfect, repeating notches. There are stones with precise T-shaped grooves running along their lengths. Others have countersunk holes, depressions with a wider opening at the top that narrows into a cylindrical shaft below, a design that appears engineered to hold a metal clamp or tie. The most baffling aspect is the consistency. These are not one-off artistic flourishes, they are standardized, repeated shapes. This repetition suggests the use of templates or jigs, guiding tools that would ensure every cut, every channel, was identical from one block to the next. To achieve such uniformity in hard stone implies a level of industrial planning we do not typically associate with antiquity. It points toward a concept that feels startlingly modern: prefabrication. Could Puma Punku have been a site of modular construction, where blocks were mass-produced to specific designs off-site, then transported and assembled like a giant Stone Age Lego set. The evidence is compelling. Detailed three-dimensional scans of the blocks reveal something extraordinary. Certain pieces, despite their massive size, are engineered to such tight tolerances that they appear interchangeable. The notches and protrusions on one block would mate perfectly with the grooves on another, locking together without mortar. This is not just precise stonework, it is a system. The countersunk holes are a key clue. They are positioned at strategic points, often on the tops of blocks. Archaeologists theorize that once blocks were placed, molten metal, likely a copper-arsenic alloy available in the region, would be poured into these holes. As it cooled and solidified, it would create a metal clamp binding two blocks together from within, an invisible, incredibly strong connection. This technique, known as metal clamping, is found in other ancient cultures, but the precision of the stonework at Puma Punku makes the system here particularly sophisticated. The function of the structure these blocks once formed remains a profound mystery. The prevailing theory suggests it was a grand platform or temple, possibly aligned to celestial events. Yet its current state is one of utter devastation. The blocks are not merely fallen, they are strewn as if by a titanic force. Some lie embedded in the ground at strange angles. This has led to inevitable questions about its demise. Does this shattered landscape record a catastrophic event, like a massive seismic upheaval or a sudden flood from nearby Lake Titicaca? Or does it suggest deliberate, systematic dismantling, perhaps by conquering peoples seeking to erase the power of the site? The technical prowess on display makes either scenario haunting. If it was a catastrophe, it toppled a masterpiece of engineering. If it was dismantling, it means someone understood the assembly well enough to take it apart, block by perfect block. This forces a sobering reconsideration. The Tiwanaku culture is dated from around 500 to 1000 Common Era, yet the skill implied at Puma Punku feels like the pinnacle of a much longer tradition. Could this site be the legacy of an even older, more advanced phase of Andean civilization, one whose timeline we have yet to fully uncover? The stones offer no easy answers, only a silent testament to a vision of order and geometry carved into the very heart of the Andes. A Roman aqueduct strides across a valley, a procession of stone arches holding a river of civilization in the air. Each arch is a masterpiece of silent calculation, a curve of perfectly fitted stones that carries the weight of mountains without a drop of mortar. This is the geometry of compression, an ancient art where precision is not just about fit, but about survival. The wrong angle, a stone cut a fraction too thin, and the entire structure would unravel in a cascade of failure. To build an arch is to engage in a high-stakes conversation with gravity itself. Structural engineers describe the principle with terms like voussoirs, the wedge-shaped stones that form the arch, and the keystone, the central, final piece that locks the whole system into place. The genius is in the taper. Each stone is cut so that its sides are not parallel but subtly angled, converging toward an imaginary point at the center of the earth. When set in place, gravity pushes each wedge downward and sideways, transferring the load through the curve of the arch and down into the massive piers on either side. The keystone, driven home last, completes this circuit of force, turning a precarious pile of rocks into a permanent, self-supporting gateway. This understanding did not appear overnight. It evolved from a simpler, older idea, the corbelled arch. In the ancient tombs of Masonry, you see this earlier logic at work. Builders stacked stones in ever closer courses, each layer projecting slightly inward over the one below, until the gap at the top could be closed with a single capstone. It creates a triangular or stepped void, a stable but space-limiting solution. The Maya used this corbelled vault to create the majestic interior spaces of their temples, a testament to its strength, though it required massively thick walls to contain the outward thrust. The Roman true arch was a revolutionary leap. By carving those precise tapered voussoirs and arranging them in a smooth semicircle, they found a way to channel the forces more efficiently. This allowed for wider spans, taller structures, and those breathtaking interior spaces like the Pantheon's dome, which is essentially a rotating arch. Later, Gothic architects pushed the concept further with the pointed arch, which directed weight more vertically, enabling the skeletal, light-filled cathedrals of the medieval era. To grasp the precision involved, walk through the mind of a master mason designing a simple arch. First, he would draw the full semicircle of the intended arch on a flat surface, his template. From this, he would determine the exact number of voussoirs. Then, using strings and compasses, he would mark out the unique taper for each stone on a rough block, knowing that every cut line must radiate from that single center point. The cutting itself, done with chisel and hammer, had to be flawless. A test fit would involve a wooden centering frame, a temporary scaffold that held the stones in place until the keystone locked them. Once that key was set, the frame could be removed and the arch stood on its own, a permanent geometry of balanced force. This was not merely construction, it was applied physics, developed through centuries of trial, observation, and catastrophic failure. How was such empirical knowledge preserved and refined across generations? It lived in the guilds, passed from master to apprentice, not through textbooks, but through the hands. A young mason learned by cutting practice voussoirs, by feeling the difference between a stone that held and one that wobbled, by listening to the stories of arches that had stood for centuries and those that had fallen. This was a cumulative tradition of tactile knowledge, where each generation could build, literally, upon the understood principles of the last. This architectural evolution from simple corbelling to the sublime mathematics of the Gothic arch represents one of humanity's most profound dialogues with the physical world, a slow, collective mastering of space and weight that would eventually point the way to spanning continents with steel and glass. Deep beneath the sun-baked plains of Cappadocia, a hidden world breathes. This is Derinkuyu, an underground city in Turkey that descends over 200 feet into the earth, a labyrinth of tunnels, rooms, and stairways carved entirely from soft volcanic rock known as tuff. It is not a single cave, but a meticulously engineered subterranean metropolis, complete with ventilation shafts that reach the surface like hidden chimneys, deep wells for fresh water, communal kitchens, stables, churches, and even wineries, all sealed from the outside world by massive, circular stone doors that could be rolled shut from the inside. To stand in its cool, silent depths is to confront a different kind of ancient precision, one defined not by celestial alignment or seamless joints, but by the profound challenge of creating a stable, breathable, and livable world in total darkness, using little more than hand picks and hammers. The engineering puzzle here is threefold: how to excavate multi-level spaces without causing catastrophic collapse, how to provide fresh air to thousands of people potentially sheltering for months, and how to orient and connect this vertical maze without the guidance of the sun or stars. Geotechnical engineers who study Derinkuyu express a quiet marvel at its stability. The volcanic tuff is soft enough to carve with relative ease, yet it possesses a cohesive strength that allows it to hold its shape when properly excavated. The builders displayed an intuitive yet precise understanding of load bearing. They left strategic columns of untouched rock to act as natural support pillars, and they carved arched ceilings, transferring weight sideways into the surrounding earth, much like the principles of a Roman arch buried in the ground. The avoidance of collapse over more than a millennium is a testament to their careful reading of the stone itself. Their techniques likely began with following natural fissures and weaknesses in the rock, using them as starter tunnels before expanding outward. To maintain level floors and properly aligned vertical shafts in pitch blackness, they would have relied on the most fundamental tools of the pre-modern surveyor, the plumb bob and the water level. A plumb bob, a simple weight on a string, would define true vertical for their air shafts and stairwells. A water level, a length of hose filled with water, would allow them to transfer a level reference point from one chamber to another, ensuring that tunnels meant to connect actually met. The functional precision of the city's features reveals a society planning for long-term survival. The ventilation shafts are a masterpiece of passive engineering. Carved at precise intervals and angles, they leverage the natural convection of air. Warm air rising out of the deep chambers would draw cooler, fresh air down from the surface through separate shafts, creating a continuous, life-giving circulation without any moving parts. The deep wells tapped into the water table far below, independent of surface sources that could be poisoned or blocked. Even the massive rolling stone doors were engineered with a brilliant simplicity, set into grooves carved into the floor and ceiling. They could be moved by a few people from the inside but were immovable from the outside, and their conical shape helped distribute the force of any impact. This raises a profound reflective question. What drove an entire society to invest generations of labor not in monuments reaching for the heavens, but in a refuge delving into the earth? The answer speaks to a harsh historical reality, the need for protection from invading armies sweeping across the plateau. Yet it also reveals a deep, intimate understanding of their environment. They did not see the soft rock as an obstacle, but as a resource, a protective blanket they could sculpt into a fortress. Their precision was born not from celestial ambition, but from communal necessity, a collective project to safeguard their entire way of life. This mastery of carving stability from the underworld represents a complete inversion of the pyramid builder's art, yet it springs from the same well of human ingenuity, turning the very substance of their world into a shield. And just as they mastered the hidden flows of air deep underground, other ancient cultures performed a similar miracle of control with the most visible and vital flow of all, water. Water is the most patient sculptor of all. While we have marveled at stones shaped by hand, we must now consider a world where water itself became the chisel, the level, and the engine of ancient ambition. This is the realm of hydraulic engineering, where precision was not merely about holding stones together, but about commanding the flow of life itself. Across continents, civilizations demonstrated a breathtaking understanding of hydrology, carving geometry into the earth to converse with rivers and rain. To stand at the edge of Chand Bayori in India is to gaze into a stone symphony of water and shadow. This colossal stepwell descends 13 stories into the ground, a breathtaking cascade of over 3,500 perfectly symmetrical steps arranged in a precise, crisscrossing pattern that frames a deep, cool reservoir at its base. Every step, every landing is a calculated part of a hydraulic machine. The design is not merely aesthetic, it is profoundly functional. The steps provide access to the water table as it fluctuates with the seasons, while the staggering depth and intricate geometry maximize shade, drastically reducing evaporation under the relentless sun. This is architecture in service of hydrology, a monument to communal survival built with a mason's precision and a physicist's mind. The true genius of such systems lies in the gradients, the almost imperceptible slopes that guide water over great distances without erosion or stagnation. Roman aqueducts snaking across valleys for miles maintained a slope often as gentle as 1 foot of drop for every 1,000 feet of length. Achieving this over-rugged terrain required surveying skills of heroic accuracy. Hydraulic engineers note that a miscalculation of even a fraction of a degree over a long aqueduct could mean the water would flow too slowly, allowing sediment to build up and block the channel, or too quickly, causing destructive erosion. The Romans used tools like the chorobates, a long water-level table, to establish these critical grades, translating a grand vision of urban water supply into a reality of stone and mortar. This mastery extended to the very cutting of the stone. In a brilliant inversion, some cultures used water as their primary quarrying tool. The concept is known as water cutting. By channeling a powerful, focused stream of water, perhaps enhanced with abrasive sand against a bedrock face, ancient workers could exploit natural fissures and fatigue the stone, causing large slabs to split free. This method would have been particularly effective in softer sandstones or limestones. Even more subtly, the constant, controlled flow of water through artificial channels could, over years, wear down and shape stone embankments and spillways with a smooth, organic precision impossible to achieve with hammers alone. The examples of this water wisdom are as diverse as the cultures that wielded it. In the arid plains of Peru, the Nazca people built the puquillos, a system of spiral stone shafts and underground aqueducts that tapped into subterranean water tables. These were not random holes, but carefully placed and angled to harness wind pressure to pull groundwater to the surface through a sophisticated understanding of air and fluid dynamics. On Crete, the Minoan Palace of Knossos boasted a complex plumbing system with terracotta pipes featuring expertly tapered joints to maintain water pressure and prevent leaks, a technology that would not be seen again in Europe for over 1,000 years. And in the sweltering lowlands of ancient Mexico, the Olmecs faced a puzzle that brings us back to the movement of massive stone. How did they transport their colossal basalt heads, each weighing 20 tons or more, from distant quarries to their ceremonial centers? One compelling theory involves hydraulic engineering on a landscape scale. Researchers suggest they may have constructed artificial causeways and canals during the rainy season, placing the giant heads on wooden sledges and using the buoyancy and lubricating power of waterlogged earth to reduce friction, then coordinating teams to pull them along these prepared, slippery tracks. This transforms the landscape itself into a tool, a temporary machine made of mud and water. This interplay between the practical and the sacred is a recurring theme. The stepwells of India were not just reservoirs, they were cool, subterranean temples for community gathering. The fountains of Roman Nymphaea were public displays of civic power and technological prowess. The Minoan pipes served both palace and ritual purification. The precision in controlling water was thus twofold: a mastery over a physical resource critical for survival, and a mastery over a symbolic element central to ritual, cleanliness, and divine favor. To command water with such accuracy was to demonstrate harmony with the fundamental order of the world. It was the ultimate civil engineering, and it paved the way for the next great frontier of ancient movement, not across land with water's aid, but across the trackless sea with a confidence that still baffles historians. The silent Moai of Easter Island stand with their backs to the sea, gazing inland across miles of rolling hills. Their journey is written in the landscape itself, a trail of fallen and abandoned giants that leads from the volcanic quarry to the island's distant coast. This is the most intimate portrait we have of the megalithic transportation mystery, a story of movement frozen in time. How do you move a statue weighing up to 80 tons across rugged terrain without the wheel, without draft animals, and without modern machinery? The answer, according to a growing consensus of experimental archaeologists, is that the islanders made the statues walk. The controversial rocking method suggests teams used a system of ropes to rhythmically rock a moai from side to side, edging it forward with each tilt, a slow, deliberate procession that could explain the scattered statues found along ancient roads. This idea transforms the moai from passive cargo into participants in a carefully choreographed dance, a feat of coordination that turns raw physics into a form of communal art. The challenge scales up dramatically with the stones of Baalbek in Lebanon. Here, in the temple complex's foundation, lie 3 blocks known as the Trilithon, each weighing an estimated 800 tons. A fourth, even larger monolith weighing around 1,000 tons rests in a nearby quarry. Moving a single one of these behemoths represents a logistical puzzle of almost incomprehensible scale. Experimental archaeology has tested the most plausible methods on smaller stones, revealing the intricate physics behind each one. The first is the sledge and lubricated track. A massive wooden sledge is built beneath the stone. The path ahead is prepared not with pavement but with a slick mixture of water and clay, or perhaps even olive oil. As teams pull with ropes, the lubricant drastically reduces friction, turning a near impossible drag into a manageable, though still Herculean, pull. The coordination required is immense, with foremen using rhythmic chants to synchronize the heaves of hundreds of workers, ensuring force is applied in a single, unified pulse to overcome inertia. The second method is the roller system. Here, logs are placed perpendicular to the direction of travel. The stone on its sledge is pulled forward onto the first set of logs. As it moves, workers behind the stone quickly retrieve the freed logs and run them to the front, creating a continuous, rolling roadway. This method is efficient but demands perfect timing and a vast supply of hardwood. The physics here is a constant battle against compression, as the immense weight of the stone flattens and splinters the logs, requiring constant replacement and a well-organized supply chain from nearby forests. Now apply these principles to history's most famous journeys. The Egyptian obelisks, single pieces of granite weighing over 400 tons, were quarried in Aswan and transported nearly 500 miles down the Nile on specially built, colossal barges during the flood season. The real feat was loading and unloading these needle-sharp monoliths without snapping them, an operation that likely involved clever use of counterweights, sand pits, and gradual, controlled tilting. Even more astounding are the blue stones of Stonehenge. These smaller, but still massive, stones were transported from the Preseli Hills in Wales to Salisbury Plain in England, a distance of over 150 miles. The prevailing theory suggests a combination of land and water routes, with the stones possibly dragged on sledges to rivers, loaded onto rafts for coastal and river travel, and then hauled the final distance overland. Each leg of this journey required a different adaptation of the core techniques, a masterclass in adaptive logistics. Picture the scene on any of these projects. 1,000 voices fall silent as the foreman gives a signal. Teams take up positions along enormous hemp ropes woven from thousands of fibers. With a deep, collective breath, they lean into their harnesses. A rhythmic chant begins, low and steady, setting the pace. Heave, rest, heave, rest. Levers creak as subsidiary teams jam wooden poles under the sledge, providing micro-adjustments to keep it on course. Boys run with buckets of water, constantly re-wetting the clay track ahead. The stone moves not in a slide, but in a series of tiny, shuddering lurches, perhaps only a hand's breadth with each coordinated effort. This is human synergy made visible, the transformation of individual muscle into a single, living machine. It was brutally hard, dangerous work, but within the rhythm of the chant, there was likely a powerful sense of shared purpose, of literally moving mountains together. This leads to a reflective crossroads. Were these methods, as ingenious as they were, the full story? Could there have been lost techniques that eased the burden, perhaps forgotten tricks of terrain? Some have wondered about the legendary idea of softening the ground, not with chemistry but with preparation. What if the routes were not just cleared but engineered? By creating a track of carefully leveled and packed earth, or even a causeway of wooden rails, the effective friction could be minimized. Other legends speak of aligning moves with frost or ice, using nature's own lubrication. The most likely answer, however, is both simpler and more profound. the lost technique was not a physical secret, but a social one, the ability to organize, motivate, and sustain thousands of people in a unified effort spanning decades. This monumental coordination was the true technology, and it was precisely this organized force that would be needed for the final, delicate act, placing these colossal stones exactly where they were meant to stand for eternity. The final shudder of a standing stone settling into its socket is a sound history has forgotten. After the grueling journey across land, the true test of ancient engineering began, the delicate, terrifying act of raising a multi-ton monolith from horizontal to vertical, and then placing another stone precisely on top of it. This was the phase where a mistake meant catastrophe, where physics had to be outwitted with nothing but timber, rope, and coordinated muscle. Construction historians studying sites from Stonehenge to Easter Island see a global toolkit of ingenious solutions, each adapted to local materials and the specific shape of the stone. The core challenge is leverage, how to apply enough controlled force to pivot an object weighing tens of tons without it slipping, cracking, or crushing the workers beneath it. One universal method involves the earth itself. For raising a standing stone or menhir, crews would first dig a sloping pit with one end deeper than the other. The stone would be dragged over this pit, its base positioned at the deep end. Using levers, teams would gradually raise the stone's head, packing stones and earth underneath to hold each gained inch. As the stone rose, the pit behind it would be filled, creating a ramp that supported its growing angle until it stood upright and could be secured in its permanent, prepared socket. This method is slow, methodical, and safe, a conversation between human effort and gravity. But for placing a horizontal lintel on top of two vertical stones, as at Stonehenge, the puzzle becomes three-dimensional. One leading theory is the timber crib and ramp. Imagine building a tall, wooden platform of logs lashed together next to the two standing sarsens. Using ropes and levers, workers would painstakingly drag the lintel stone up this earthen and timber ramp until it rested at the very top, positioned exactly between the two uprights. Then, with a series of smaller levers from below, they would nudge the lintel sideways off the platform, inching it horizontally until it slotted onto the carved tenons on top of the uprights. Every movement would be minuscule, every shift checked and stabilized. On Easter Island, the challenge was different, raising the already carved moai statues onto their ceremonial platforms, or ahu. Here, oral tradition and experimental archaeology point to a method called parbuckling. The statue, lying on its back, would have ropes passed under its belly and up over a high, temporary timber framework. As teams pulled on the ropes from the front, the statue would pivot on its belly, its base swinging downward toward a prepared pit while its head rose majestically toward the sky. The ropes provided mechanical advantage, and the timber frame acted as a fulcrum, allowing a relatively small team to lift a colossal weight in a controlled, rocking motion. The precision required in the preparatory work was absolute. Before any raising began, the stone's final socket had to be dug with exacting care. At Stonehenge, the sockets for the sarsen stones are not simple holes, they are shaped, with one side sloped to guide the stone's base into its final position. The stones themselves were often shaped for the fit. The famous Stonehenge lintels have mortise holes carved into their underside that lock onto tenons or rounded knobs carved on the tops of the uprights. This is Neolithic joinery on a gargantuan scale, ensuring stability without a speck of mortar. To understand the sheer coordination, walk through an experimental reconstruction of raising a menhir. A 15-ton granite slab lies beside a dug pit. Teams lash ropes around the stone's upper third, anchoring them to stout wooden stakes driven deep into the ground behind it. Others position long timber levers under the stone's head. On a signal, the lever teams push down in unison, their poles creaking under the strain. the stone's head rises a few centimeters. Immediately, a separate crew darts in to jam wooden blocks into the new gap. The lever teams relax, reposition, and heave again. The stone rises another few centimeters, more blocks are inserted. Meanwhile, teams on the anchor ropes take up slack, preventing any dangerous backward slip. This cycle repeats for hours, perhaps days, the stone rising in a slow, steady arc until gravity finally takes over and its base slides down the prepared slope of the pit, thudding home into its socket with a finality that must have felt like a thunderclap. This moment of successful erection was far more than a construction milestone. For the community that achieved it, it was likely a profound ritual, a physical manifestation of bringing order from chaos, of connecting the earth to the sky. The collective breath held as the stone tipped, the roar of triumph as it settled true, these were the sounds of a society defining itself through shared endeavor. The successful raising of these stones speaks to a deep, intuitive understanding of balance, a knowledge written not in books, but in the synchronized movements of 100 pulling arms and the strategic placement of a wooden wedge. It was the culmination of every earlier technique, from quarrying to transport, focused into one perfect, precarious act of equilibrium. And this mastery over balance and mass finds its ultimate expression not in stone, but in the creation of spaces that manipulate perception itself, where the architecture seems to defy the very rules it was built upon. Before a single stone was cut, the builders faced a blank canvas of sand or bedrock. Their first and most critical act was not physical labor, but celestial observation, using the sky itself as a ruler and compass to inscribe perfect geometry onto the chaotic earth. This initial layout, the ghostly blueprint drawn with shadows and starlight, determined the destiny of everything that followed. Archaeoastronomers and modern surveyors studying these sites have reverse-engineered methods that reveal a breathtaking fusion of naked-eye astronomy and practical geometry. To establish a true north-south line, essential for structures like the Great Pyramid, Egyptian priests likely used a simple but brilliant technique centered on the circumpolar stars. These are the stars that, from a given latitude, never set below the horizon, circling the celestial pole. By observing a single star's rising and setting points over the course of a night, and marking the midpoint between them on the horizon, they could find a line pointing directly to true north. A tool called a merkit, a notched palm rib with a plumbob string, acted as a primitive but highly effective sighting instrument. One priest would sight a specific star through the notch of his merkit, while an assistant placed markers on the ground along the line indicated by the plumbob. By repeating this over several nights, they could refine the alignment to an astonishing degree of accuracy. For an east-west line tied to the sun's path, they employed methods like the Indian circle. Imagine driving a vertical pole into the ground. As the sun rises, the pole casts a long shadow to the west. You trace the tip of that shadow with a circle drawn in the sand around the pole. As the sun climbs, the shadow shortens, then lengthens again in the afternoon. The moment the shadow's tip again touches the circle marks a point directly west of the pole. Connecting that point to the pole's base gives you a perfect east-west line. This solar geometry, combined with the stellar north line, created a sacred cross on the landscape, the foundational axis upon which an entire cosmic order would be built. The proof is in the monuments themselves. The Great Pyramid of Giza is aligned to the cardinal directions with an error of just 3/60ths of a single degree. To put that in perspective, it is a deviation of less than the width of a human hand over the pyramid's entire 230-meter base. This is not a lucky guess, it is the result of meticulous, repeated observation. Across the ocean, the city of Teotihuacan in Mexico presents a different celestial puzzle. Its central avenue, the Street of the Dead, and the surrounding grid of temples are not aligned to true north, but are deliberately skewed 15.5 degrees east of north. Researchers have found this orientation aligns not with Polaris, but with the setting point of the Pleiades star cluster on a key date in the Mesoamerican calendar, and also corresponds to sunrises on days that divided their ritual year. Here, the grid was laid down not for abstract cardinality, but as a terrestrial map of a specific celestial event, embedding their cosmology into the very streets they walk. We can almost witness the ceremony. At a chosen site under a canopy of stars, the chief priest and his surveyors perform the stretching of the cord ritual. They chant, aligning their sighting rods with a star's graceful arc. Assistants scramble to place limestone markers where instructed. By dawn, a perfect square, aligned to the 4 pillars of the world, is pegged out on the desert floor. This act was far more than surveying, it was a sacrament. It wove together practical necessity, religious cosmology, and the vital science of calendar making into a single gesture. The foundation was now consecrated, a piece of the ordered heavens fixed upon the earth, ready to support a weight of stone meant to last for eternity. This celestial groundwork, however, would be meaningless without an equally precise system to manage the staggering human effort required to bring the vision to life. The seamless joint between 2 stones is a line of perfect unity, an idea made solid. This obsession with precision forces us to confront a question that echoes louder than any tool mark. Why was this flawless work simply the best way to make a wall stand? Or was it a language, a way to speak to forces beyond the physical world? This is the great divide in understanding our ancestors, the split between seeing them as master engineers and as high priests of geometry. Anthropologists who study these cultures remind us that for many, the act of building was itself a sacred ritual. To construct with perfection was to create a mirror of the cosmos, a small, ordered world that reflected the harmony of the gods. In this view, a seamless joint was not just about keeping out the weather, it was a symbol of societal unity, of a community without cracks. An alignment to the solstice sunrise was not merely a calendar, it was a divine umbilical cord, a moment when heaven touched earth through a gateway of stone. The specific proportions of a temple, often based on sacred numbers or geometric ratios like the golden mean, were not aesthetic whims, they were believed to resonate with the harmonic principles that structured the universe itself. The building was an instrument tuned to a cosmic scale. We can see this tension between the purely functional and the deeply symbolic in stark contrasts across the ancient world. The Roman road is a masterpiece of pragmatic precision. Its layered foundation, cambered surface, and drainage ditches were engineered for one purpose: to move legions and commerce efficiently across an empire. Its beauty is in its ruthless utility. Now, step into the confined space of a pharaoh's burial chamber deep within a pyramid. The granite walls are polished to a mirror finish, the joints are invisible, the sarcophagus fits its niche with uncanny exactness. This precision served no practical structural purpose hidden from view, nor did it aid in the chamber's function as a final resting place. Its purpose was transcendent, to create a perfect, eternal vessel for the king's spirit, a space so flawlessly crafted that it belonged to the realm of the imperishable stars. The precision here was a spiritual technology. This fusion of the technical and the symbolic manifests in astonishing ways, like the phenomenon of architectural acoustics. At the base of the Mayan pyramid of Kukulkan at Chichen Itza, a single clap of hands produces not a simple echo, but a chirping sound that eerily resembles the call of the Quetzal bird, a sacred creature associated with the feathered serpent god for whom the pyramid is named. Was this a miraculous accident of stone placement and stair geometry, or was it an intentional acoustic design, engineered by builders who understood how sound waves would reflect off the massive stepped facade? For a culture that saw the world as deeply interconnected, where ritual chant and ceremony were bridges to the divine, crafting a temple that literally sang with the voice of a god seems not just possible but profoundly meaningful. It suggests a mindset where physics and faith were not separate disciplines, but two sides of the same sacred coin. So where does this leave our search for understanding? Can we, with our modern categories of science and religion, ever truly separate the technical from the spiritual in the minds of these ancient builders? The very attempt might be a mistake. For them, building a stable wall and honoring a cosmic principle may have been the same act. The precision was the point because it demonstrated a harmony with the natural order that was both physically resilient and spiritually correct. The perfect joint proved mastery over stone, but it also proved reverence for the material and the geometric ideals it represented. This pursuit of meaning in the masonry brings us to the most human element of the mystery, the individuals whose hands, minds, and hearts translated this unified vision from thought into enduring stone. His hands were the first to touch the stone and the last to leave it perfect. We have marveled at the monuments, but we have forgotten the man, the anonymous master whose calloused fingers felt the grain of granite and knew exactly where it would yield. Who were these individuals, the minds behind the miracles? Were they revered priests speaking the language of the gods? Were they members of powerful artisan guilds, their skills passed down like royal treasure? Or were they a unique class of philosopher-engineers, blending sacred geometry with the gritty reality of a quarry? The truth is likely a fusion of all three, a social and intellectual identity we struggle to categorize. Social historians piecing together clues from tomb inscriptions and administrative records paint a compelling picture. In ancient Egypt, the title of chief builder or overseer of all the king's works was one of immense prestige, held by individuals who were often literate, skilled in mathematics, and of high social standing, sometimes even relatives of the pharaoh. They were not mere laborers, they were the CEOs of antiquity, responsible for a portfolio that included astronomy, logistics, material science, and managing a workforce of thousands. Their knowledge was a form of power, carefully guarded and transmitted. This secretive expertise almost certainly flowed through a tightly controlled system of apprenticeship, where a young boy would enter a master's service, learning not from scrolls, but from silent observation and hands-on correction. The complex formulas for mortar mixes, the precise angles for an arch, the rituals for aligning a temple, these were likely preserved in oral tradition, encoded in songs, chants, and myths to protect them from being lost or stolen. We catch glimpses of these legendary figures in the rare instances where a name survives the millennia. In Egypt, the name Imhotep echoes through history. Originally the chief architect for Pharaoh Djoser, designer of the first pyramid, he was later deified as a god of wisdom and medicine. His legacy tells us that the greatest builders transcended their profession to become cultural heroes. In the Andes, the creator god Viracocha is described in myths as a wise teacher who instructed humanity in the arts of civilization, including architecture, before walking across the waters into the West. These stories may preserve the memory of a real foundational figure, a master whose techniques became the bedrock of a building tradition. To understand their daily reality, let us walk for a moment in the sandals of a pyramid site architect at Giza. His day begins before dawn, not with a chisel but with a problem in logistics. A report arrives that a shipment of limestone from Tura is delayed because a barge ran aground. He must recalculate the work schedule for the western face, shifting teams to interior corridor work instead. Later, he meets with the chief quarry master to examine a crack in a granite block destined for the king's chamber, deciding whether to salvage it or abandon months of work. In the afternoon, he walks the growing perimeter with his surveyors, using his knotted cords and sighting rods to check the alignment of the latest course, knowing a deviation of a finger's width now will become an arm's length error by the summit. His mind juggles sacred geometry, human fatigue, political pressure from the vizier, and the unyielding physics of weight and stone. He speaks the language of numbers to the scribes and the language of the gods to the priests, for in his world they are the same. This concentration of knowledge in a small, elite group leads to a haunting reflective question. What was truly lost when these traditions were interrupted by invasion, famine, or social collapse? How much profound understanding of materials, of seismic dynamics, of celestial mechanics was held in the minds of a few master builders and never written down? The loss may be incalculable. An entire library of empirical science could vanish in a single generation if the chain of apprenticeship was broken, leaving behind only the physical stones as a cryptic testament to a wisdom we must now painfully reconstruct. Their ultimate legacy, therefore, is not just in the monuments that stand, but in the silent challenge they pose. They force us to redefine intelligence, to see that deep mastery of the physical world can flourish without our modern tools, rooted instead in observation, patience, and a unified vision that saw no divide between a perfect joint and a perfect prayer. Archimedes once declared that with a lever long enough and a place to stand, he could move the world. He was not describing a new idea, but giving voice to an ancient one, a principle of physics that master builders had been using for millennia to perform their own terrestrial miracles. The secret to moving mountains was not magic but mechanics, the brilliant, deliberate application of simple machines. Before the age of engines, human ingenuity discovered 6 fundamental tools that could multiply force and redirect effort: the lever, the wheel and axle, the pulley, the inclined plane, the wedge, and the screw. In the hands of ancient engineers, these became the building blocks of the impossible. Consider the lever, the most fundamental of them all. A long, sturdy timber placed under a stone acts as a force multiplier. The pivot point, or fulcrum, is positioned close to the load, while workers apply pressure to the much longer opposite end. The mechanical advantage is immense. A small downward push at the far end translates into a massive upward force capable of lifting a corner of a multi-ton block just enough to slip a roller underneath. This is not speculation, it is basic physics, and the wear patterns on ancient stones often show the telltale pry marks of lever points. Once the stone was lifted, wooden rollers, essentially primitive wheels and axles, could be placed beneath it. A sledge carrying the stone would then glide over these rolling logs, reducing sliding friction to a fraction of its normal value. To make the system even more efficient, evidence suggests they used lubricants, water, clay slurry, or even animal fat poured onto the track ahead of the moving mass. The combination of rollers and lubricant transformed a seemingly impossible drag into a coordinated, rhythmic pull. The most visible and grandest simple machine of all was the inclined plane, the ramp. To raise stones to the soaring heights of a pyramid's upper courses, builders constructed colossal earthen ramps that snaked up the growing faces. These were not mere piles of dirt, but engineered structures, often built with a core of rubble and faced with plastered mud brick to create a stable, smooth surface. The ramp's gentle slope traded distance for effort, allowing teams to drag a sledge upward with a manageable, sustained force. Archaeologists have found remnants of such ramps at Giza and other sites, their very existence a testament to this pragmatic, monumental solution. The wedge, a portable inclined plane, found its purpose in the quarry, where workers would drive rows of wooden wedges into pre-cut channels in the bedrock. Soaking the wedges with water caused them to swell, generating tremendous, controlled pressure that split the stone along a clean line. Now, apply these principles to a specific, iconic challenge, raising a Stonehenge lintel. Picture a 25-ton sarsen stone needing to be lifted 20 feet into the air to rest atop 2 uprights. One compelling method involves a compound system, a timber frame acting as a giant lever and fulcrum. The frame is erected beside the uprights. Ropes are passed over its apex and attached to the lintel, which lies on the ground. As teams pull on the ropes, the frame redirects their horizontal pull into a vertical lift, a primitive form of pulley system. The mechanical advantage is significant, perhaps allowing a team of 50 people to achieve what would otherwise require hundreds. The lintel rises in increments, each small gain held fast by wooden blocks until it reaches the precise height needed. Then, with smaller levers from atop the uprights or from a temporary timber platform, the stone is nudged horizontally, an inch at a time, until its mortise holes slot perfectly onto the tenons below. This entire operation is a symphony of simple machines, a physical algorithm executed with ropes, wood, and stone. This practical genius forces a reflective shift in perspective. The awe we feel before these ancient sites should not stem from a belief in lost super technologies, but from a profound respect for the human mind's ability to maximize the potential of simple tools. It demonstrates that innovation is not always about inventing something new, but about seeing the profound capabilities hidden within the ordinary. A lever is just a log, a ramp is just a pile of earth, but in the context of a unified vision and coordinated labor, they become the keys to reshaping the world. This mastery over fundamental physics connects directly to an equally sophisticated understanding of the environment, a knowledge of how to harness local materials and natural forces not as obstacles, but as partners in construction. The perfect stone was born, not made, deep within the earth. Long before a chisel ever touched its surface, the entire process of ancient precision hinged on a single, critical decision made in the dust of a quarry. It began with the discerning eye of a master, a person who could read the mountain like a book. He would walk the exposed rock face, his fingers tracing subtle variations in color and grain, his ears attuned to the sound of his hammer's tap. He was searching for a vein of granite or limestone free of hidden fissures, inclusions, or weak planes, a flawless canvas for the work to come. This was not random selection, it was applied geology, a deep, inherited knowledge of material properties that determined the destiny of an entire project. These builders understood that stone had a personality. Some types, like the fine-grained limestone from Tura across the Nile from Giza, could be cut with relative ease yet weathered to a hard, durable shell, perfect for a pyramid's gleaming casing stones. Others, like the red granite from Aswan, were chosen for their immense strength and symbolic power, destined for the eternal chambers of a king. They even selected stones for acoustic properties, knowing that certain rocks would ring true when struck, a sign of internal soundness, while a dull thud might betray a hidden flaw that could cause a block to fracture under stress. This simple tap test, listening for the clear ring of a healthy stone, is a technique still used by stonemasons today, a direct link to that ancient sensory wisdom. To extract these perfect blocks, they worked with the stone, not just against it. Geologists studying ancient quarry sites see a consistent, intelligent method. The quarry masters first identified natural fracture lines in the bedrock. Then, using stone or copper tools, they would laboriously cut a narrow channel, perhaps just a few inches wide, along the desired line. Once the channel was deep enough, they would drive a series of dry wooden wedges into it. Then came the water. As the wood absorbed the moisture, it swelled with tremendous, even pressure, slowly and cleanly forcing the block to separate from the living rock along the pre-weakened plane. This method of channeling and wedging minimized waste and shock, preserving the integrity of the stone. The scale of this operation becomes staggering when you visit the quarries themselves. At Aswan, the unfinished obelisk still lies in its granite bed, a single piece that would have been the largest ever erected at over 1,000 tons. It was abandoned when a catastrophic crack appeared in the stone, a permanent lesson in the risks of quarrying. All around it, the landscape is scarred with the evidence of extraction, with trenches and tool marks showing where dozens of other colossal obelisks and blocks were successfully freed. Far to the south, the quarries that supplied the andesite for Puma Punku tell a similar story of mass production, with precise, geometric blocks seemingly popped from the earth like teeth from a jaw. And then there was the logistics. The finest materials were rarely local. The Tura limestone had to be ferried across the Nile. The Aswan granite traveled nearly 500 miles by barge. The bluestones of Stonehenge came from over 150 miles away in Wales. This implies a supply chain of breathtaking sophistication, a system that could identify a resource, mobilize the labor to extract it, transport it across treacherous terrain or water, and deliver it to a distant construction site, often years later, with the expectation that it would fit a predetermined plan. This was more than mining, it was a covenant with the landscape. It forces us to ask, what kind of relationship did these cultures have with the earth they so expertly plundered? They possessed a localized environmental knowledge so profound it feels instinctual. They knew which hillside yielded the most resonant stone, which riverbank clay made the best mortar, which season provided the best conditions for transport. They treated the earth not as an inert resource to be conquered, but as a living partner in a grand, collaborative act of creation. The perfect block resting in the quarry was just the beginning. It was a promise of potential, waiting for the next, even more demanding phase of its transformation. The final stage of ancient construction was not a rough assembly, but a transformation of touch. Run your palm over the polished limestone wall of an Egyptian temple or the carved surface of a Mayan stela, and you feel a surface smoother than modern poured concrete, a finish so fine it seems to defy the very nature of stone. This mirror-like perfection was the culminating act, a testament to a civilization's commitment to see a project through to absolute completion, where every visual and tactile detail whispered of mastery. Achieving this was a science of abrasion, a patient dialogue between human persistence and granular earth. Conservators who study these surfaces under microscopes can read the story in the stone's skin. They see the faint, parallel striations left by the polishing agents, each telling of a different stage. Initial grinding with coarse quartz sand would remove the larger tool marks. Then progressively finer grits, perhaps crushed emery or even powdered hematite, were applied with water using flat stones or leather pads in a circular, methodical motion. The final act was burnishing, where a smooth, hard stone or a pad of felt was rubbed with immense pressure and speed, generating heat that fused the microscopic particles on the surface into a continuous, glassy skin. This was not a quick process. Experimental archaeology reveals the staggering effort. To polish a single square foot of granite to a high sheen using only sand, water, and a stone rubber could take a skilled worker days of uninterrupted labor. The achievements are breathtaking in their diversity. In Mesoamerica, artisans created obsidian mirrors with surfaces so flat and reflective they could cast a clear image, a feat requiring control over one of the most brittle and fractious stones known. In Egypt, the interiors of some granite sarcophagi and boxes were polished to a near-liquid gloss, a finish that served no structural purpose hidden deep within a tomb. And across cultures, this perfect stone canvas was often the foundation for further art, covered in painted stucco or intricate reliefs that depended on that flawless, stable base to survive the centuries. This obsessive final touch forces a reflective question that goes beyond mere technique. Was this brilliant polish purely for beauty, a visual celebration of human craft? Was it functional, creating a surface that shed water and resisted the accumulation of grime? Or was it profoundly symbolic, representing a state of ideal completion, where the rough, chaotic material of the earth had been elevated into a permanent, luminous form worthy of the gods or the eternal soul? Likely it was all three. The polish was the final seal on the covenant between builder and material, the point where the stone ceased to be a rock and became an idea. It represents the culmination of the entire precise process, from celestial alignment to the last loving stroke, a silent declaration that nothing less than perfection would suffice. The final polish on a stone fades with the last generation to know its secret. We stand before these monuments and ask not only how they were built, but why the knowledge to build them seems to have evaporated from history. The disappearance of these techniques is a story of collapse, not of tools, but of the delicate social ecosystems that sustain them. Imagine a vast, living library where the books are not written on papyrus, but held in the minds of master builders, the rhythms of their chants, and the muscle memory of their apprentices. Then a prolonged drought parches the land, a volcanic winter chokes the sun, or a wave of invasion shatters the political order. The library, in a very real sense, burns. Historians of science point to a sobering truth. In pre-industrial societies, high-precision craft traditions were astonishingly fragile. They depended on a stable, stratified society with a surplus of food and labor, a powerful central authority to commission projects, and most critically, an unbroken chain of apprenticeship that could span centuries. When that chain snapped, the knowledge it carried vanished, often within a generation or two. The potential historical pivots are stark. Consider the late Bronze Age collapse around 1200 before Common Era, when a perfect storm of drought, famine, seismic activity, and mass migration brought the great palace economies of the Eastern Mediterranean to an abrupt end. The art of cutting and fitting massive ashlar masonry, so prominent in Mycenaean Greece and Hittite Anatolia, largely disappears from the archaeological record for centuries. The knowledge did not simply walk away. The social and economic structures that required and nurtured those elite guilds of stonemasons disintegrated. In the Americas, the arrival of Spanish conquistadors did more than conquer empires. It dismantled entire knowledge systems. The intricate understanding of astronomy, geometry, and stonework possessed by the Inca and Maya was not merely suppressed, it was rendered functionally obsolete within the new colonial order. The great building projects ceased, the master craftsmen were killed, dispersed, or forced into new trades, and the oral traditions that carried the technical secrets slowly faded into legend, surviving only as cryptic fragments in the stories told by elders. Even without sudden catastrophe, knowledge can evaporate through a gradual shift in priorities. As societies move from building eternal monuments for gods and kings to more pragmatic, rapid construction for commerce and housing, the incentive to spend a lifetime mastering the perfect stone joint disappears. The techniques for moving megaliths, for example, might not have been lost in a single disaster, but simply abandoned when no one needed to move a 100-ton block anymore. The specialized tools were recycled, the crews disbanded, and the nuanced physics of leverage and lubrication, once common knowledge on a work site, became forgotten lore. We can speculate on a specific loss at a site like Göbekli Tepe in Turkey, a mysterious complex of carved stone pillars built over 11,000 years ago by hunter-gatherers. The society that erected these stones possessed a sophisticated understanding of quarrying, shaping, and erecting multi-ton monoliths. Yet, after the site was deliberately buried and abandoned, that knowledge seems to have left no direct lineage. What precise method did they use to transport those T-shaped pillars from quarries hundreds of meters away? Was it a technique of rolling on logs, or perhaps a clever use of hide ropes and earthen ramps that was never recorded, never passed on because the cultural imperative to build in that way simply ended? The knowledge likely fragmented, surviving in diluted forms in later, simpler construction methods, or transforming into mythic tales of giants or gods who built the old stones. This forces a deeply reflective question about our own age. We live in a world of digital archives and global networks, believing our knowledge is permanent. But are we equally vulnerable? Our most advanced engineering and manufacturing techniques are often held by a small number of specialists and encoded in software and machinery. If a major, prolonged disruption severed our supply chains and energy grids, how long would the practical knowledge to build a microchip or a precision turbine survive? The loss of ancient techniques is a mirror, showing us that knowledge is not a static possession, but a living process that requires a society healthy enough to sustain its transmission. This sobering contemplation of loss naturally turns our gaze forward, to the modern workshops and laboratories where a new kind of builder is trying to reclaim what time has erased. The past is not a static museum, but a living workshop where the stones themselves are the final exam. To move beyond speculation, a new breed of researcher has emerged, the experimental archaeologist. These are not just scholars in libraries, but engineers in hard hats, stonemasons with calloused hands, and volunteers willing to spend months doing what ancient builders did for a lifetime. Their mission is disarmingly simple, yet profoundly difficult: to rebuild the ancient world using nothing but the tools and materials available at the time, and in doing so, to test every theory we have ever proposed. This field is our most direct conversation with the past, a physical dialogue where success is measured in inches moved and stones fitted. The results are often humbling, revealing not the simplicity of ancient methods, but the staggering depth of skill they required. Take the iconic Moai statues of Easter Island. For years, theories abounded about how these giants were transported. Then, a team led by archaeologists Terry Hunt and Carl Lipo decided to test the most plausible idea: that the statues were made to walk. With a concrete replica and teams of volunteers pulling on ropes, they demonstrated that by rocking a moai from side to side in a careful, coordinated rhythm, a surprisingly small group could indeed inch the multi-ton figure forward across the landscape. The experiment was a success, but it revealed the immense, precise coordination needed. A single mistimed pull could topple the statue, a lesson likely learned the hard way by the original builders, as the scattered, fallen moai along the ancient roads silently attest. These modern endeavors are filled with such revelations, where failure teaches as much as success. Another team attempting to replicate Inca-style polygonal masonry discovered that the process was far more than cut and try. Selecting the right hammerstones was critical: dense, hard river cobbles that would not shatter on impact. They learned that an abrasive slurry of sand and water was not just helpful, it was essential, acting as a grinding paste that slowly wore down the high spots with an efficiency that pure pounding could never achieve. Most importantly, they documented the sheer time and teamwork involved. Fitting two irregular stones together was not a linear process, but a three-dimensional puzzle solved through constant communication, tactile feedback, and a willingness to remove just a tiny bit more stone, again and again, over weeks of labor. The most ambitious of these reconstructions was a project documented by Nova, in which a team of Egyptologists and modern masons attempted to build a small, 6-meter-tall pyramid using only ancient Egyptian tools and methods. The challenges were relentless. Quarrying the limestone blocks with copper chisels and stone pounders was agonizingly slow. Moving them on a wooden sledge required a perfectly prepared track of wet silt to reduce friction. The act of raising the blocks, even to this modest height, demanded ingenious ramp designs and lever systems. The project was a masterclass in practical problem solving, but it also highlighted a gap between modern experiment and ancient reality. While they succeeded, the pace was glacial compared to what the historical record suggests for the Great Pyramid. This gap is where the true insight lies. Our struggle to replicate these feats, even with our understanding of physics and our ability to plan, tells us something profound about the ancient world. It was not a world of primitive effort, but of refined, cumulative expertise. The master mason at Giza did not need to experiment with different hammerstones. he knew from a lifetime of apprenticeship which ones worked best. The foreman moving an obelisk did not guess at the optimal rope tension. He knew the rhythms and chants that synchronized 200 men into a single pulling machine. The knowledge was embedded in the culture, passed down through generations, becoming as instinctual as it was technical. These experiments are therefore more than academic exercises. They are bridges of empathy. By straining at the same ropes, by feeling the same blisters, by experiencing the frustration of a stone that will not fit, we gain a visceral appreciation for the intelligence and perseverance of those who came before us. We stop seeing them as mysterious others and start recognizing them as peerless engineers, whose greatest technology was not a forgotten machine, but a perfected system of human knowledge, cooperation, and relentless will. This modern dialogue with stone leads us inevitably to the final, overarching question that has shadowed our entire journey, a question about the very nature of progress and what these silent monuments are trying to tell us about our own place in time. The jigsaw walls of the Andes and the star-aligned pyramids of the Nile are not isolated wonders, but chapters in a single, global story of human ambition. Our journey across this landscape reveals that the ultimate secret was not a forgotten machine or an alien blueprint. It was something far more profound and entirely human. The true foundation of these impossible structures was a triad of genius, profound observation of the natural world, generations of cumulative experimentation, and an extraordinary capacity for social organization. Our ancestors did not possess superior tools. They possessed a superior understanding of how to use them. They turned the constraints of their era, the lack of iron, the absence of engines, into a catalyst for innovation. With nothing but stone, sand, water, and timber, they engaged in a patient, physical dialogue with the very elements, learning to listen to the song of the rock and the rhythm of the stars. Their constructions were more than buildings. They were conversations with the cosmos, etched in granite and limestone. These sites stand today not as dead ends for our curiosity, but as open invitations. They ask us to look closer at the world around us, to question the simple narratives of progress, and to appreciate the quiet, relentless ingenuity that has always been a part of the human spirit. They remind us that mastery is not defined by the complexity of your tools, but by the depth of your understanding and the unity of your purpose. So we leave you with a question to ponder. Which of these ancient techniques captures your imagination the most? Is it the earthquake-proof puzzle of the Inca, the celestial clockwork of the pyramid builders, or the mysterious molded stones of forgotten sites? Share your thoughts in the comments below. And if you crave more journeys into the unexplained, where history's greatest enigmas are patiently unraveled, be sure to subscribe. Our next exploration into the shadows of the past awaits.